A gigantic ball of gas hugging so close to its star it looks like an egg. A world that absorbs so much light it's darker than coal. A wet, rocky body just at the right distance, a form of life might call it home. These are just some of the many planets known to orbit stars other than our Sun. Astronomers call them exoplanets. Finding these planets is a challenge all in itself, but getting to know some of the characteristics that make them so diverse, their sizes, shapes, and what they're made of, is an even greater one. To take on this difficult task, a European partnership composed of 11 countries, co-led by Switzerland and the European Space Agency, built Cheops, a small planet watcher satellite that orbits Earth and looks at worlds we already know surround bright stars, to get to know them even better. Because exoplanets are very hard to see directly, hidden by the bright glare of the stars they orbit, astronomers mostly do not try to do it. Neither will Cheops. Instead, it will look for the effects those planets might have in the light coming from the stars they orbit. As a photometer, an instrument that measures light, Cheops will measure starlight with incredible precision and focus on two big goals. Very accurately measure the sizes of small planets. Discover more about the atmospheres of big exoplanets orbiting very close to their stars. Additionally, Cheops may even give us hints of the existence of more alien objects, like exomoons or exorings. To accurately measure the sizes of planets, Cheops will use a method called transit photometry. When a planet passes in front of its star, the so-called transit, it blocks a very small part of the stellar light. For a brief moment, that star gets dimmer. And how much dimmer it gets depends on the size of the planet relative to the star. Planets come in a lot of different sizes, and the bigger planets block more of the light that reaches us, and smaller planets less. These are tiny changes, but measuring them with Cheops allows astronomers to figure out exactly the size, the radius, of a planet. Cheops is unique because it focuses specifically on planets with known masses to precisely measure their size. Together, the size and mass of a world make it possible to know its density. That way, even without being able to see exoplanets directly, we already have vital clues on their compositions. Are they rocky planets like Earth, or gassy like Jupiter? Are they water worlds, or small icy balls? Cheops' other main goal focuses on giant gassy planets that live recklessly close to their parent stars. Astronomers call them hot Jupiters. Cheops can measure how the light coming from a star changes as planets like these orbit around it, in a way like the different phases of the Moon. These measurements are called phase curves and tell us the amount of light the planet reflects or absorbs. It's albedo. A planet's albedo reveals important information about its atmosphere. It can answer questions like, does this planet have clouds? What are they made of? How hot is this world? For example, a planet with white clouds, like Earth, reflects more light than one with darker clouds. Used by astronomers in Europe and worldwide, Cheops will play a crucial role in studying the hundreds of fascinating worlds in our galaxy. It will lead the way for the instruments that follow and point out the best targets to be studied more directly. It will uncover vital clues about the formation and evolution of planets, and perhaps leave us one step closer to discover where we come from and whether or not we're alone in the universe.